So, all right, welcome back for the last talk of the morning session. We have Konrad from the University of Bristol, and he's going to talk about streams and bounded-deletion.
Okay, thanks everyone for coming, and thanks for inviting me to speak. Good. So this is about matchings, and it's about streaming. So we have seen quite a lot on the topic before, but yeah, let's review the models first. So the model we look at is, so there are basically two models that are relevant. There's the insertion-only graph stream model. So in this setting, we see essentially a sequence of the edges of the input graph. We do a single pass over the data, and we compute the output to a problem. Now, to observe is that the stream length here is at most n square, where n is the number of vertices of the graph. So this has been significantly studied, this model. But there's also a insertion-deletion model. So in this setting, besides edge insertions, we have deletions as well. So here in this example, we see, for instance, that we have, so that's not a pointer, I realize. We see that we have actually a sequence that describes the exact same graph. We just see, for instance, that an edge that's highlighted E5 is inserted, and deleted again. So in the end, it doesn't even make it in the final graph. But we can have these insertions and deletions over and over again. And what makes really a difference is that the stream length here can be unbounded, because we can play these games of inserting and deleting over and over again. So it's certainly a bit harder to deal with. Now, generally what we want is algorithms that use less space than sort of trivial, less space than n square. Good. Now we focus on the maximal matching problem. So we have a graph here. Then in the middle we see a matching, so a subset of edges that are vertex disjoint, and then we see a maximal matching. So maximal matching is one that can't be trivially extended by just adding an edge outside the matching to it. And here we see a relatively big one, but they can be much smaller as well. In essence, they just need to block all the other edges in the input graph. Good. So in insertion-only streams, that's not a particularly hard problem. So in insertion-only streams, if we don't have any deletions, we can just run the greedy matching algorithm that was observed a long time ago. We start with an empty matching for each edge in the stream. We insert the edge into the matching if that's at all possible, if it isn't blocked yet, and we return the matching. So this creates a maximal matching, solves the problem with space at most n log n. And yeah, that's good. We need that much space to write down a matching. That's optimal. There's no debate about it. So this is, in insertion-only streams, very clear. The setting is very clear for maximal matching. So the question then is, what do we do in insertion-deletion streams? So if we have these deletions in the stream as well. So it's not quite so clear what kind of technique we could use in this setting. I mean, we can't greedily add edges somehow and then hope that they're not deleted later on. So these techniques won't translate. And we know, for instance, randomization can't be avoided in these settings. We know even if you had the problem of just outputting a single edge from the input stream deterministically, then you would need space n square for that. So even if you just want to report an edge, that's actually quite hard already deterministically. So clearly, these deterministic strategies don't work here. So we've also seen this quite a few times in this workshop. So the main technique are basically linear sketches in insertion-deletion streams. So essentially, we pick a sketching matrix at random, project everything down to a small sketch, and sort of maintain the sketch while we process the stream. And indeed, essentially, almost all insertion-deletion algorithms that we know of, they are essentially linear sketches. To the point that we know that under some conditions, for instance, we need very long streams. Algorithms need to be able to process very long input streams. We know that linear sketches are universal in the sense that you can essentially design, given an algorithm, you can design one that it just maintains a linear sketch and produces the same output as the other streaming algorithm. So linear sketches, it all points towards basically linear sketches being the technique for insertion-deletion streams. So the question is, can we use this for maximal matching? And the answer is not really. So maximal matching, we have a lower bound. In insertion-deletion streams, it requires space n square. So we can't really get a sublinear space algorithm for maximal matching. Okay. Yeah, good. So we have basically these two situations. In insertion-only streams, space n log n. In insertion-deletion streams, we have space n square. But what we're interested in is there not anything in between these two models, because we have either the absence of all deletions, or we go immediately to a situation where we have an unbounded number of deletions. So what happens in between? So what we do is we parameterize the number of deletions by an integer k. And then we might ask, what is the space complexity of essentially maximal matching in the presence of at most k deletions in the stream? So what could possibly happen? Well, it could happen that, well, we just interpolate nicely between n log n and space n square, and depending on k, this gives a nice smooth trade-off. But we could also have some sort of phase transition. Maybe there's a threshold where suddenly the complexity jumps. So these are basically the situations that we want to sort of see and determine what happens here for maximal matching. Good. Okay, so what's I find quite interesting is that this seems to be the first work really that explicitly addresses these bounded deletion graph streams. So up to a minor comment, which I'll talk about on the next slide. So first of all, why should we study this setting? So it appears, at least to me, and I don't know that much about the practical world, but it's certainly the case that growing data sets, every growing data set certainly must have more insertions than deletions. Otherwise, the data set wouldn't grow. So in some sense, bounding the number of deletions seems a very sensible thing to do. It's also, in some graph settings, it seems quite naturally that we have insertions, but not that many deletions. If we really think about friendships and networks and things like that, they are usually created, but not necessarily as often deleted. So it seems to capture quite some number of applications. Now, regarding sort of previous work from our area, so bounded deletion streams have been very explicitly studied. There's this paper by Jairam and Woodruff. They look at sort of more these statistical problems like heavy hitters, L0, L1 estimation, and they observe that basically there is a log n gap between these two when you go from insertion only to insertion deletion. So they do essentially, they bound indeed the number of deletions, not quite as directly with a fixed parameter, but they look more at the ratio of the number of deletions in the context of the number of insertions. And they see that you can replace this log n gap by sort of a log alpha gap, where alpha relates sort of to the density of the number of deletions in the relative to the number of insertions. We have also a work in the sort of in the graph world, graph streaming world. There's a work by Kormod et al. For matching size estimation in bounded aberricity graphs, and they essentially have an algorithm that just works really nicely when you bound the number of deletions. So it's not really targeting explicitly the bounded deletion setting, but it translates quite well into the setting. But I believe this sort of concludes, at least to my best knowledge, the literature on that topic. Okay, so why is it that there are not more works about bounded deletion streams? And I don't know why really, but I think there's this inherent kind of seemingly the equivalence between insertion deletion streaming and linear sketches. So we immediately jump to linear sketches when we think about insertion deletion streams, and for very good reason, because linear sketches are really useful in the setting. They can just naturally handle essentially an unbounded number of deletions. As soon as you go to the linear sketching world, you insert and you delete, you insert and delete. None of this is naturally handled by linear sketches. So in some sense, once you work with linear sketches, there's just no reason to bound the number of deletions, because this is inherently naturally covered by linear sketches. But what this also means is, when we go to bounded deletion streams, if we want to design something that's better, we really have to go beyond linear sketches. We can't just use linear sketches, because then they would apply for the general setting, and in the general setting, we are basically in the insertion deletion setting. So we must do something beyond linear sketches to save some space. Okay, so now when it comes to maximal matching, what should we expect in terms of this parameter k, the number of deletions? So, Andrew? Total number of deletions overall. Thanks. So I mentioned we have this lower bound. Maximal matching requires space n square. So let's just unpack this a little bit, so how this is proved. So the technique for establishing this lower bound was just one-way two-party communication. So the setting that is used for proving this n-square lower bound is Alice holds edges, sends a message to Bob. Bob holds deletions, and the deletions have to be a subset, of course, of the edges that Alice holds. And Bob outputs essentially a maximal matching. And if we just see this, we believe that there's an n-square lower bound coming out of this. The fact that Bob holds a subset of the edges of Alice, and they're at most n-square edges, means that this lower bound would never use more than n-square deletions. So as soon as you reach n-square deletions, k equals n-square, we know that basically space n-square is necessary. So this limits immediately sort of the range, the interesting range for the parameter k for us to study. So we know the interesting parameter for k, range is between 1 and n-square, basically, for k. So the question again then is, what do we do in this range? Okay, so this brings me to the results that we have. So again, number of deletions k and number of vertices of the input graph. So we have a one-pass bounded deletion streaming algorithm that uses space O tilde n root k and computes a maximal matching. So the dependency that we get is root k here, n times root k. We also have a matching lower bound. So space n root k is also needed. So we can prove that this is best possible for this problem. So this means what we have is basically a smooth trade-off. So it does go nicely from sort of if k is constant or small, then we have space O tilde n, like in the insertion-only model. And if k is n squared, then we exactly end up at the insertion-deletion setting. So it goes nicely. There's a smooth trade-off. Sipper?
Or it holds for order 1 approximation also?
It would hold for order 1 approximation also, yeah. Mm-hmm.
Study a bit unrelated, but like, what's the size of the matchings in these lower bounds? Is it n?
Theta n. Yeah. So if there's time, I time to talk for 30 minutes plus 5 minutes talking on the lower bound. So if I can get it in, then I talk about it as well. Okay, good. Yeah, so I want to talk mostly about the algorithm, and if time allows, I talk a little bit about the lower bound. So the algorithm, let's first think about somewhat general considerations. So we want space n root k. Now n root k is always omega of k for every k smaller than n square, and that's sort of the range that we're interested in. So we can actually, within the space bound, just collect all the deletions as we see them in the stream. So that's what we do as well. So we have the deletions, all of them in memory at the end when we get to the end of the algorithm. Then just for this talk, think for a moment about the situation where first all edges are inserted, and then only at the very end we see the deletions. That's not something we need. We can handle arbitrary streams, but for this talk, it's a little bit easier to think about it this way. Now, the tools we use, we got 2 tools, 2 main ingredients into this algorithm. So the first one are hierarchical greedy matching. We call them like that. And just this technique alone, so I'll talk about it in a minute, would bring us to space n times k already. Then if we add now a second technique, which we call it's a sort of a matching repair data structure, and we add it to that, then the 2 together, they allow us to get down to the space n root k. So let's talk first about these hierarchical greedy matchings. So we will run in the actual algorithm, we will only run this algorithm on the substream of edge insertions. So ignoring all deletions, just we focus on the substream of edge insertions. So the algorithm is really simple. It's probably what you would expect immediately when you hear the term of hierarchical greedy matchings. So it's parameterized by an integer L. We compute L matchings overall. We go through the stream and we try to insert every incoming edge. First, we try to insert it into M1. If it doesn't work, we try M2. If it doesn't work, we go to M3 and so on. And if we can't insert it into any of the M1 to ML, we just discard the edge. We don't store the edge. So this builds sort of a level or hierarchy of matchings. Now, what is nice about this structure that we compute is, so you can see this quite nicely if there are no deletions at all. So assume for a second there are no deletions at all. Then you can actually take each of these matchings, mi, and you can extend it within the structure to be globally maximal. Because as such, mi wouldn't be maximal for any I. M1 is maximal for sure, because this coincides with the greedy matching. Mi itself wouldn't be maximal. But you can extend it as follows. So we know that every edge that's either in mi+1, mi+2, or even hasn't even made it into the hierarchical matching, we don't have to worry about, because we have tried it actually to insert it into mi. It didn't work, so it went into a different matching, or it was discarded. So that the vertices of mi, they're basically a vertex cover in E minus the matchings M1 to mi-1. So we only have to be worry about the edges that are in M1 to mi-1, but we can just try to greedily add those now to the matching mi, sort of insert those. And if we attempt to do that, then we see basically the resulting matching we get must be maximal, because we've tried to sort of, by construction, it must be maximal. Good. Now, suppose now we have k deletions, and let's run the algorithm with L equals k+1. So we construct one more level than the number of deletions, then we know there must be a matching in this collection that isn't subject to any deletions. Now, the same argument applies. We can now make the same point. So all the other edges that have arrived that are not sort of M1 to ML-1 that are beyond, we tried to insert it into ML. It didn't work, so we don't have to worry about maximality. And the deletions really don't affect the structure at all. It's even better for us because there are fewer edges left. So this means just doing that, well, we get already a deterministic bounded deletion algorithm with space n times k, because we have k levels that we need to use here. Okay. Any question on this? No. Okay, so but we need something more, because we want to go down to space n root k. So, oh, I guess the tilde would be, it depends on whether you store words or bits, and yeah, there's not more to it. So there will be more that comes in for the upper bound, so there's certainly some log factors involved that will be hidden, yeah. Okay, so we use also a matching repair data structure, and it will be, the intuitive meaning of that is exactly what it sounds like. We delete some edges, and we have to repair sort of the deleted edges back, so that will be the purpose of it. So in the end, what we do is we run the hierarchical greedy matching on root k levels, and we store in parallel, as we process the stream, a matching repair data structure on roughly the same number of edges, so also roughly n root k edges. Then we pick a matching in this hierarchy that was subject to at most root k deletions. And we can do this. So we do this in a post-processing stage. We don't need to do this earlier. So we know exactly, since we know all the deletions, we can pick such a matching. And then we just repair it back to be globally maximal using this matching repair data structure. So what is this matching repair data structure? So in essence, we fix one deletion at a time. And to fix one deletion, we only need O tilde n edges. So in fact, we will see that this matching repair data structure, once you fix one deletion, you just copy this structure. You do the same process root k times in parallel, and this will fix all deletions. So once you understand sort of one deletion, then it's not very difficult to going to repairing k deletions. And I think what I find quite interesting is that this is sort of the linear sketching part of the algorithm. So the hierarchical greedy matching is clearly not a linear sketch. This is the part that's deterministic, that, you know, certainly not a linear sketch, but this part is. And in particular, these edges that are stored in a matching repair data structure, they're completely independent of the matching itself. So, but still, nevertheless, they work in order to repair basically any matching. Oh, I mean, you could run algorithm A1 and compute the hierarchical matching, and algorithm A2 to compute this, and they have nothing to do with each other in that sense. Yeah. Good. Yeah, so repeat this root k times to fix all deletions. Okay, so let's focus just on the subproblem of fixing a single deletion. So we have our matching, and there's an edge UV, and in the end, there's a deletion, and we have to delete this edge. So we will repair the vertex U and V separately. And so let's just focus on the vertex U. So generally, you would need to make sure that the edges incident on U are sort of dealt with. They are blocked, or we have to maybe rematch U. That's sort of the most intuitive fix that we could possibly have. But there's an observation. So imagine we managed to store, while processing the stream, we managed to store the entire neighborhood of U for some reason. Then we're in a really good position, right? If we actually know the entire neighborhood around U, we could either rematch U to a currently unmatched vertex, And if we can't rematch U, well, then we're good anyway, because then the edges incident on U, they don't violate the maximality of the matching. So our goal will be to use sort of this property. We want to know about vertices where we know the entire neighborhood. So here's a first attempt using space n root n, and then we see that we can reduce this to space n a bit later. So do the following. For each vertex that we have, just sample theta tilde of root n random incident edges to that vertex. That's the first approach. And then on top of that, pick a subset of vertices v1 and of size root n, and for those ones, store their entire neighborhoods. So that's a very simple linear sketch, and this can be implemented with L0 sampling, for example. Then, okay, so what's going to happen? So let's have two cases. First case, suppose the degree of U is actually just O tilde root n. Then, you know, for every vertex, we already stored root n incident edges. We're done. We know the entire neighborhood, so we're good. So there's no problem in this case. So the interesting case is really when the degree of U is larger than root n. So in this picture here, we see that, yeah, so U and V, the edge is deleted. Now, maybe we're just lucky, and we stored an incident edge here to an unmatched vertex. That would be perfect. We just rematch U, and we're lucky, and that's also great. So the tricky case is more if actually all the edges incident on U that we stored in our data structure, they point towards already matched vertices. So in this case, the edges incident on U, they should illustrate basically the data structure F. So these root n or root n tilde, theta tilde of root n incident edges that go to matched vertices. Now, the interesting thing to look at is basically their mates now of these neighbors. So U goes into this neighborhood, but then all of these edges are matched. So looking back at their mates in the matching, there are, of course, also root n or theta tilde of root n such vertices. But then we know that we also computed, we selected a subset of random root n vertices. And we know that, and for those, we stored the entire neighborhood. So we know basically one of those neighbors of U among the edges that we stored, there must be some V prime, such that V prime is connected to some U prime. U prime must be in V1. We know the entire neighborhood of this vertex in V1. So the key idea is basically to shift the blame of rematching from U to this vertex U prime. So we eliminated the edge U prime V prime, rematched U to V prime, and now our task is basically to worry about U prime to rematch this vertex. But then this is easy by this observation that we had. We know the entire neighborhood.
Would you need to recurse this because V dash has all of its neighbors matched, and then if you go one more level, you might be able to do it. Will that happen?
I didn't quite understand what you meant.
I was just asking, like, let's say you start from U, and it turns out all of its neighbors are matched, and you look at the vertex V dash and ask, are you, like, do you have a neighbor who's unmatched, right? Sorry, what I'm trying to say is, you look at all of its neighbors. Would they need to look at their neighbors and so forth?
Yeah, you're alluding to exactly the right thing. So in this setting, we only have basically two levels. We were always guaranteed that we find basically in the neighborhood someone who's matched to someone where we know the entire neighborhood in this situation. But to bring the space down, what we do next, we have indeed many more levels, and you might form longer chains like that. But in the end, you're going to end up at a vertex where we know the entire neighborhood. But in this case, I think this is all that is needed.
So you said we sample root n vertices and keep all of their neighbors?
Yeah.
Is this n root n or?
We sample root n vertices, and each neighborhood is of size n.
But couldn't this be more than n root k?
Oh, yeah. No, sorry. This is a first attempt to fix one deletion. We use space n root n for that. I'm going to bring now down the space down to n for this task, and then we fix root k deletion, then it's n root k. Yeah. Mm-hmm.
Why is V1? Maybe what is V1? Define this.
Why is?
What is V1 and why is it that vertex in V1?
Oh, okay. I mean, the idea is really just, you know, the vertex U stores at least root n, say, incident edges. So if you look at their mates, there are also root n incident mates. Now, if you sample root n random vertices from your graph, then you're going to hit one, basically, with decent probability. Yeah. Mm. Yeah. Good. Okay. Now, yeah, so basically, to bring this down to space n, what we need to do is We start with V0. We say V0 is the entire vertex set, and then we go down always by a log factor. So V1 would be n over log n, V2 is n over log square n, etc. So we decrease by log factors in size. But then for each I, in VI, we store basically log to the, well, here I plus 2 works, n incident edges. So if you go down in VI, you store always a log factor more edges, so the sum will still be O tilde n. So you get log n over log n layers. And in particular, we know that in the last layer, the entire neighborhood is known of the vertices. So we have this nice property that we wanted. And now we could go through the exact same argument again, but I'm probably going to just not walk you through this again. But what basically is going to happen is, if we want to rematch the UV, we want to rematch U, and we start with V0, then we have basically the same argument. There must be an incident edge such that the mate is in V1. There must be an incident edge such that the mate is in V2. And we can basically go through the layers all the way until we, along the way, we might be just lucky and find a good edge that where we can rematch anyway, but we are guaranteed that if we go all the way to the end, we will have the entire neighborhood stored for this vertex. And this will do the job.
The algorithms randomly.
Correct, absolutely. Yeah, that's right. Mm-hmm. Good. So the algorithm summary is essentially we have just hierarchical greedy matchings on root k levels. We store all the deletions. We pick a matching that is subject to at most root k deletions. And we replicate this matching repair data structure 2 root k times to fix both incident vertices. And that's essentially it, and gives us our result of n root k for this problem. How much time do we have left, roughly? 4. Perfect. Good. Then I just want to show you how this lower bound is obtained for this situation. So we know, again, so there's the DK20 lower bound that says that maximal matching requires space n square, and we mentioned already earlier, it's proved in the one-way two-party communication setting where Alice holds edges, Bob holds deletions, and the output is generated afterwards. Now, the way this lower bound really works is that Alice holds a random bipartite graph with edge probability 1/2. Now, Bob has these subsets A prime, B prime, which here, let's say they are, say, 1/10 of the entire bipartition each. And then apart from A prime, B prime, so Bob doesn't delete anything in here incident to A prime and B prime, but it looks at the induced subgraph down here between A minus A prime and B minus B prime, deletes absolutely everything except one large induced matching. That's essentially the lower bound that we get. And it turns out that if you wanted to report a constant fraction of these blue induced matching edges, this requires space n square to do. Yeah. It has to report, absolutely. Size estimation wouldn't work here for these lower bounds. Yeah, absolutely. Thanks. Yes?
What exactly does identify mean here?
Report, output the edges. There is an edge between this and this vertex in the end. Yeah. Mm-hmm. And yeah, so we use this lower bound. So there's a very easy first attempt what you could do. If I should also say we have n square deletions here because the subgraph is just big enough. We have a random graph. There are lots of edges. So there would be theta of n square deletions to turn this graph into a sparse graph with one induced matching here. So that's a problem. We want to get the number of deletions down to k. So the first thing we could just try is, well, let's scale down the instance. Instead of n vertices, n by n, we have just use root k vertices on the left, root k vertices on the right. Then we surely have only k deletions, but we get only a lower bound, space lower bound of omega of k in that case if you just use a scaled down version. So we immediately, so dk20 implies a lower bound of omega of k immediately without doing anything. So the next idea would be to say, okay, we only use so far square root k vertices, but the graph is n vertices. So let's repeat this gadget independently n over root k times. Then, well, if we do that, then we get actually our lower bound, n root k space lower bound, because we have an omega of k lower bound for one instance. We repeated n over root k times. This gives us our n root k lower bound. But the problem is that the number of deletion increases because every single copy itself has k deletions. But then, well, you should give the talk. This is exactly what we're doing. This is a very simple observation. Essentially, the picture that comes with the situation that I've illustrated is that Alice holds this disjoint graphs and root K graphs, and then Bob turns those into, instances where we have these large induced matchings at the bottom, but has deleted everywhere. And indeed, what Sipper said is exactly the observation that you need to do. Instead of turning all of those into, subgraphs with one large induced matching, you can just pick basically a uniform random one of those, turn only this one into, delete only in one of them, because, well, the algorithm has to report maximal matching in all of them. If you pick a uniform random one, the message sent from Alice to Bob needs to contain enough information that allows Bob to still identify in one uniform random instance, basically a maximal matching. So, yeah, Andrew?
Sorry, I didn't mean to interrupt.
No, it's fine.
We also said that this low boundedness extends to kind of constant approximation. And I don't see how that would work if I only delete on one instance.
That's a good point. Good. Yeah, I see. Yeah, it might not. You're right. Oh, good. Thank you. Thanks. Yeah, good. So this is essentially the enter technique, and then the index j is unknown to Alice. That's basically a direct sum argument that we would get here. So implementing this is basically just one last comment. The DK20 lower bound, the way it's established, is basically a reduction to an augmented index problem in the end. So where Alice holds a long bit string, Bob holds the suffix of the bit string and needs to output sort of one specific position. Now, what we do is a slightly more involved version of an augmented index problem, where instead of one bit string, we have r bit strings. But then Bob has this one index I that selects one of these instances, one index j as an augmented index, the respective suffix, and you just need to report this one bit. And then essentially relatively standard arguments, information theory arguments, allow us to prove this lower bound of r times t. And the final reduction is then very, very similar to the DK20. Yeah, but to summarize, so the space complexity of this is basically n root k. This is our main result, both upper bound and lower bound. For future work, there is essentially a lot that would be very interesting to know. So I would classify problems in there are problems that are significantly harder in insertion deletion than insertion only. So in particular, approximate maximum matching, approximate vertex cover. So for these problems, it's very unclear to us what the right answer is. But there are also a lot of problems that are almost identically hard in both models. They differ only by log factors. But I think even there, it would be really interesting to know what happens, whether there's some jump in, where the threshold of the number of deletions is, where you end up in the insertion deletion setting. And yeah, I think all of these questions would be very, very interesting to figure out. And that's it. Thank you.
To follow up on what Andrew said, it is plausible then that there is an algorithm with n plus k as space and gets order 1 approximation of matching.
So I know an algorithm that uses space k that gets an order 1 approximation. This basically follows from, you can use this hierarchical greedy strategy you can only use the hierarchical greedy without the repair data structure to get a constant factor approximation.
Oh, so then your lower bound was really not working. It's not
Yeah, I don't know why I said that. I take this back.
Just do 10K edges in hierarchical greeting, then you will get order.
Yeah. Mm-hmm. Yeah, if you just
if you just do something like 10K, 10 plus 10K edges or so in the hierarchical greedy, order n plus k edges in the hierarchical greedy, you will basically have one match which will lose less than constant factor, and you can just pretend you repaired that constant factor and work down. Okay. Yeah. And that will just get.
Yeah.
So the hierarchical greedy matching thing was deterministic and got O of nk, but the lower bound it seems also holding to randomize the n square root k. So if it's deterministic, is nk like an obvious lower bound also?
It's definitely not an obvious lower bound. No. Mm-hmm. This is a good comment, yeah.
Is it known what the lower bound is for deterministic? Is it different?
No. I mean, we know, I think if you have k deletions, then you need at least space k to even report an edge deterministically. So k is an obvious lower bound, but beyond that, yeah.
Can you go back to the lower bound slide?
Sure.
Maybe like a few more. So what's the role of these smaller subsets of vertices that you delete, that you do not delete their edges? Why not just delete, just pick one matching from the random graph and delete everything else?
Oh, that would be easy. If you're left in a graph with just one matching of size n and nothing else left, there are only n edges in the graph, you can just do sparse recovery or something, you can find it. So they definitely need to, they keep the graph dense and yeah, hide basically this matching well enough. Mm-hmm. Yeah.
So if you consider the model that you can delete, you can have k edge deleted, but you can repeat it. So what I'm saying is the total number of distinct edges is k, but in principle you could have many more deletions.
Right. Mm-hmm. Mm-hmm. Just they repeat on the same set of k edges, these insertions and deletions.
So would this lower bound of n squared hold, or?
I mean, my guess would be that we can design the same kind of upper bound. We get also n root k as an upper bound. The lower bound already holds when we have only k deletions. So I don't think we need to repeat. I don't think it makes the problem harder. I think it's more upper bound question to see whether it works in our setting, and I would believe it does. But yeah, I don't think the lower bound would help for getting a better lower bound. Yeah. Mm. Yeah.
And would the problem change if? So you want to return the matching, yes?
Yeah, absolutely.
If you care only about the size.
Yeah, that's a difficult one. No, I think generally we don't know so much about size estimation. So these, in particular, these lower bounds really rely on reporting edges. Like we really need that for these lower bounds. So yeah, this would be, it's very different. I suppose the situation could be very different. Mm.
Maybe our last question. So if you allow more than one pass, what happens?
It's something to be studied. The question is about having more than one pass. It's not clear in this bounded deletion setting, at least, what the trade-off exactly is. Yeah. Mm-hmm.
Any other questions?
You have lots of open problems on whether one can get something for other terms. Is there some naive or easy black box upper bound approach that just works for all of them? So you have a benchmark where it starts to become interesting. So if you can deal with k deletions, and if you know a good algorithm for insertion one, you can automatically get something that looks.
I see what you mean. I don't think I can see something like that. Like, is there an insertion-only algorithm that, with some blow-up, if k is known, would immediately translate into a bounded deletion algorithm? I don't see that. It might be very problem-specific. So, yeah, but it's possible. I don't know. Mm-hmm.
All right. So that's question again.
Thanks.